So in 8.5, we're using exponential and log functions, which we've already done some of this in 8.4. Our focus is going to be on exponential growth and decay equations. So continuous exponential growth, the only difference between these is f of x equals and y equals. You just have to have one of them, okay, ae to the kt power, or y equals ae to the kt power. So you'll see either f of x function form or you'll see your y. Really, that should be your f of t. So your a is still the initial value. Your t is time. Okay, and then this variable k is the growth rate constant. So if it's constant, that means it doesn't change for a given set of values. Okay, so we're going to use that equation to represent different real-world scenarios. Often it's used with population growth. It is the same as the continuously compounded interest formula. It's just instead of A, we use Y. Instead of P, we use A. And then instead of R, we're going to use K. So in this section, what I am assessing is your work with logs. So this note is that every problem needs to be solved algebraically. So you have to show that work with logs, okay, in order to get credit. And because we have E, what log undoes E? Do you guys remember the name of that from last week? The natural log, yes, so that ln. Okay, so we're going to use the natural log, that ln, to solve. Okay, so that's your ln. All right, so in our first example, it says the initial population of rabbits in an area is 8,000, and the population grows continuously. So that lets us know that we're using our continuous exponential growth. And they give you the rate of 26% each year. Okay, we have to write an equation that represents the rabbit population P in thousands after T years. Okay, so when you're writing that equation, it's important to pay attention to the variables they give you and what they represent. So the rabbit population is P, but it's in thousands. Okay, and that's going to be after T years. So if you know your initial population is 8,000, but you want to write that in thousands, do you guys know what you would do to solve? Yeah, just divide by 1,000 and your value for A would be 8. Okay, so this is going to be our value for A. Okay, if they give you 26%, that's the rate of 26%, we're going to write that as a decimal. That is now the value of K. That's your rate of continuous growth. All right, so then when you plug those into your equation, you will have P is equal to 8e to the 0.26t. Okay, so whenever you are making your own equation, you are going to be plugging in the value of A and K. Right? Sometimes people try to plug them in for P or T as well, okay? But you will not have that because you need to have an input variable and an output variable. All right, in example 2, it says an experiment starts with 20 bacteria A cells. So there's going to be a bacteria B. Okay, so 20 bacteria A cells. After 45 minutes, there are 710 bacteria A cells. We are going to write an equation that models the number of bacteria A cells after T minutes. Okay, so when you are writing a model, you are going to have to plug something in for A and K in your final model. Okay, but you may have noticed they do not give you a rate this time. So if they do not give you a rate, you are going to have to find it. Okay, you're going to have to find K. So what I like to do is I like to start by organizing the information they did give me. So if it starts with 20 bacteria, I know that's my initial value. Okay, so I know my A value is going to be 20. And then it says after 45 minutes, there's 710. So what that means is when your value of time is 45 minutes, that output value, Y, is equal to 710. I'm just going to have to write that again. 710. Okay, so you have to use that given information to find K. And when we do find K, we're going to round to 5 significant figures. Is that something you guys have talked about maybe in a science class before? The significant figures? Okay. All right, so for the value of Y, we're going to insert 710. The A value is going to be 20. Okay, and it's 710 after 45 minutes. Okay, I want you to see if you can do the first 2 steps. Okay, if you weren't here on Friday and didn't do your notes yet, that may be a little more difficult. Okay, so yep, grab your calculator if you don't have it out. If you need one, let me know. Okay, so Lorelai, what do you think is our first step to solving here? Yep, so your first step is to divide by 20. That's going to isolate that value of E. So then you have E to the power of K times 45 is the same thing as 45K. So sometimes I'll rewrite it like that. Okay, and then I will reduce it if they both end in a 0 because that's something we can do quickly. You could also write it as 35.5. You just don't have to. That's up to you. Okay, and then once we get here, Cody, what's our next step? Yep, so it won't be times, it'll just be taking it. So you're going to take the natural log, okay? And the reason why you do that is because when you take the natural log of E, what happens? Yeah, they cancel. Do you remember last week we talked about how it equals 1? And we use the power rule. So once you have the natural log, you can write this exponent in front. And then I said it was okay if you didn't write like times natural log of E because we know that's going to be 1 anyway. And then your last step to get K by itself is divide by 45. And really, I don't write that again. You could write it again and then divide. Or if you just want to plug that in there, that's fine. So we're going to round this to the nearest, well, 5 significant figures. So could be to 5 decimal places. Could be more depending on what we have. Sorry, I'm in polar mode here. Okay, so we're going to do the natural log of 71 divided by 2. Make sure you close your parentheses. And then sometimes I'll do enter and then I'll divide by 45. That part doesn't matter. So if you have a 0, it's 0.0, and then we'll do 5 digits from there. 7932. Okay, and thanks. Yeah, sorry. And then this is your growth constant. Let me get my whiteout pen. And I didn't mean 5 significant figures. I meant 4 significant figures, and that's why we're doing it to 5. So normally we round it because when we're doing the logs, remember how we were always rounding to the nearest 10,000? Yes, for all of your homework things, it was the nearest 10,000, right? 4 decimals. Okay, and then this one though, if you go to 4 decimals and they are not significant figures, I want you to go out to 1 more. Okay, so do the 10,000 unless it's not the significant figure. So we're going to keep it like this. Four decimals or 4. And thank you guys for helping me with that one. Okay, and then we're going to write our model. And remember, the word model and equation are interchangeable here. So you're going to have y equals, your a value is 20, and then it's e to the 0.07932t. So this equation that we started with, that same thing, except we are plugging in values for a and k. All right, which is just what we wrote down here. You're plugging in those values for a and k. All right, and then in part B, it says, after how many minutes will there be 1,000 bacteria A cells? Anytime they're asking you how many minutes or how long, that's an indicator that you're trying to find the time. Okay, so you're going to find T. They tell you there's going to be 1,000 bacteria A cells. What are we going to plug that in for? Yes, that's your Y. So find T when the output is 1,000. Okay, so you have your model. It's right here. I want you to plug that in and see if you can do the first couple steps. Okay, so you're going to plug that in, do the first few steps. All right, so you have 1,000 equals 20e, 0.07932. Okay, and then Megan, what'd you do first for this one? Good. And when you divide, okay, you do not have to reduce. I will, though, if it's both ending in 0, because then I just have 100 divided by 2, so that's 50. Okay, and then Alex, what do we need to do at this step?
So natural log.
Yep, so we're going to take the natural log because we want that to cancel out. So when we take the natural log, that brings the exponent down in front. And then to get t by itself, we just divide by that value in front. Okay, and then like I said, instead of having you to write that out again, if you just want to leave it and then divide it, that's fine. Okay, you're going to be doing this several times. It's going to hopefully become a memorization. You divide, you take the log, you divide. Okay? All right, and then Kanan, when you have that decimal, will you round it to the nearest hundredth for me? Yep, 49.332. Yep, okay. And then with the story problems, I always want you to include the units. Okay, so this is going to be minutes. All right, nice work. All right, part C is going to be a little bit new. So this says bacteria B grows exponentially according to the model, and we are going to fill in the model. So according to the model, y equals 52e to the power of 0.064t. Okay, so they're giving us this model. So y equals 52e to the 0.064t. Okay, and then it asks after how many minutes will there be more bacteria A cells than bacteria B cells? We're going to round that to the nearest tenth. Okay, so it says after how many minutes? So we have to find the time. Okay, we are going to find the time when the bacteria A is greater than bacteria B. Okay, so if I set this up, I'm going to use my model found in part A. That represents bacteria A, 20e to the 0.07932t. And I want to find t when that value is greater than bacteria B, which is 52e 0.064t. Okay, so we have an inequality here. Normally, what we would do is we would divide by that front number, but we can't do that because we have e's on both sides. So what we're going to do is we're going to take the natural log of both sides. Yes, yes. I'm going to take the natural log here. We'll go ahead and squeeze that in there. I guess I wrote it in the next step and then I forgot. Okay, and then what we're going to do is we are going to use the product property to rewrite it. Okay, so you might remember from last week, we were introduced to those properties, right? The product, the quotient, the power. So the product property says if you have two things multiplied together, that you can rewrite it with what? Addition. Yeah, you can do that too. That would be the power. So 20 times this value of e to that power, we can rewrite as the natural log of 20 plus the natural log of E to the power of 0.07932t. Not that I'm aware of, but I can tell I'm also running out of room.
0.079.
And I'm gonna try to squeeze mine in here. So I have the natural log of 52 plus, I'm gonna write it down here, natural log of E 0.064t. Need to not write so big here. Okay, now if you do that, do you guys think you know what our next step is going to be? We're going to do that after we do something else first. We are going to subtract and add things, but first, we can cancel those out, right? The natural log and E, don't those operations undo one another? Uh-huh.
So it kind of looks like it's a line, if you cross it out with a line. It looks like it's called a line. Like without an N.
There. It does kind of look like it spells that. So this will be the natural log of 20 plus 0.07932t. And then that's going to be greater than the natural log of 52 plus 0.064t. Yeah. The natural log of E, those are going to cancel out. And now we're going to get anything with the variable to one side. So see how I have t here and I have t here? So we want them all on one side. Does not matter which side you move them to. My strategy is to try to move them to where the t is going to be positive. Okay, so we calculate that for me. You can use your calculator. Maybe longer. Okay, now because we moved all the t's to this side, let's go ahead and move the natural logs to the other side. Okay, so minus the natural log. So this is going to be the natural log of 2 minus the natural log of 20. Now we are just using that to calculate, so if you want to leave it like that, you can. Do you guys remember another way that you could write that? $52 over what? Yep, so either one. And then your last step is just going to be to divide by 0.01532. Okay, and if you want to write that out a little quicker, remember I said you could use the decimal, that would be fine. Okay, and then we're going to round that to the nearest tenth. And then will you put your units on that as well? All right, and then Bella, what'd you get for your final value? 10th. Okay. All right, so 62.4 minutes. That's the hardest thing we'll do today, in my opinion. Second page. All right, we gotta do decay. No, we cannot. Well, let's just get through it. All right, so with the exponential decay, the most common application is the half-life. Okay, so the half-life is really what it sounds like. It's the time it takes for a substance to be cut in half. And by that we mean its mass, right? So if it starts with 30 grams, right? After the half-life it would be 15. Okay? All right, so then your two equations, you can either have f of x equals ae to the negative kt or the y. Okay, so your A and T are going to be the same as with your growth model, but now the K is the decay constant, and your Y value is your amount remaining. All right, so the first thing we're going to look at is chromium 51. That has a half-life of about 28 days. And we're going to determine the value of K and the equation of decay for chromium 51. So we're going to find the value of K and the equation. Okay, so what we're going to use is that the time is 28 days. That's your half-life. If they do not give you an initial value, you can choose your own.
Use one.
Yep, and that's what I'm going to use. No initial value is given. Choose your own. Okay, so Jackson said, can you use one? Yes, I think one is the simplest one to use, so that's what we're going to use.
Are there situations where it's better to use not one?
No. You can't choose 0 because then it doesn't exist. Okay, so I'm going to choose 1 milligram. I chose milligrams because that's what they're going to use over here. Okay, you don't even have to specify the unit in this one. So that means after 28 days, how much is going to be left? No, half a milligram. After 28 days, your Y value is going to be half of a milligram. And again, you can choose whatever value you want. We're going to talk about why. So if you're plugging this in to your equation right here, okay, you have Y equals, so 0.5 is equal to 1 e to the negative k times 28. Okay, the reason why I like to use 1 is because 1 times anything is just going to be the same thing. So this is equivalent to e to the negative 28k. And then what can I do right away? Yeah, I can just take the natural log. Okay, so let's say you picked my favorite number, 8, and you started with 8, okay? Then the half-life would be After 28 days, how much would you have left? 4. Okay, so then when you did this, your first step would be to divide by 8. 4 divided by 8 is 0.5. See how you're at the same place? And then you take the natural log. Okay, so no matter what, you're going to end up with this situation. So if you choose 1, it's just like you're multiplying by that value. Okay, and then we know that ln undoes e, so the negative 28k comes down, so we can divide both sides by negative 28. Okay, so we're going to find our decay constant, and it's either 4 decimal places or 4 significant figures. Okay, so we're going to do the natural log of 0.5. Make sure you close that parenthesis, or you will not get the same thing. Okay, so 0.0247, and then that 5 is going to be pushed up to a 6. Okay, so this is the decay constant, which is what they asked us to find, the value of k. Okay, and then we are also going to write out the equation of decay. So when you write out the equation and you don't have an a value, you can just write it as y equals ae to the negative 0.02476 t, and then you just have to specify what t is measured in. So where t is the time in days. All right, so I want you to read through part B and see if you can set up and calculate what part B is asking you for. Okay, so one thing to note is that it's asking you how much. Okay, so how much will be left after 30 days? If they're asking you how much is going to be left, then they're going to ask you to find y, when, and they give you 2 pieces of information. They tell you the sample is 650 milligrams. So what's that going to be plugged in for? A, and then 30 days is going to be T. Okay, so when A is 650 and T is 30. So you have already wrote down the model. Now we just have to find Y when A is 650 and plug in 30. Okay, we'll round to the nearest hundredth for this. Okay, Nihal, let me know what you get when you calculate that to the nearest hundredth. Try it again. Let me see what you're getting. You like that? All right. And when it doesn't say what to round to on your homework, you can decide. So if you rounded to the nearest tenth for this, that's okay. And then this is going to be milligrams because it's the amount. All right. And then for the last one, it says how long will it take for that sample to decay to 200? And that does say round to the nearest 10. Anytime it says how long, that means we're going to find what? T. Okay, so then we're going to find T when, so this is still your initial value. And then if it decays to this much, that is your final amount. Okay, so we're going to plug in 200 as our value of Y. 650 is the initial value. And then we have E. Okay, so when you are solving for time, you are going to be using natural logs. Okay, so the first thing we want to do is get E by itself. So we're dividing by that value in front. Okay, and then you can feel free to just leave this as 20 over 65. You don't have to worry about reducing it all the way. Okay, it's just so that when you're putting that in your calculator, you can do something simple to reduce. You have that. Okay, remember that those cancel, and then you have to write that this comes down. Okay, like I said, you're going to be doing this several times, so you're going to get in the process. And when you've practiced it enough, your brain is going to go faster than your pencil, and that can be frustrating for us. Okay, but you need to make sure you're writing down these important steps, okay? So now we're doing the natural log of 20 divided by 65. Okay, and then if you're writing it over here, I said it was okay if you just put those quotes to show that you're dividing by that same value. Okay, and then this did say to round to the nearest tenth, so 47.6, and then this is measured in days. Yeah. All right, I want you to read through example 4 and see if you can set up part A without me. It's a little trickier, that's okay. All right, so what's different about example 4? Yes, they gave you a percent. And look at this substance, this radioactive substance has a half-life 24,110 years. Long time. Okay, and they also give you the decay constant. Okay, so it's asking you again, how long will it take? So we know that we have to find a value of t. Okay, so how long will it take to have 75% of the sample remaining? All right, well, we know that we have to find t. Okay, we are not given an initial value. So one way you can think of this is think of the original sample as a value of a. You could also just pick out any value that you wanted. That would be fine as well. Okay, but if your original sample is a, if 75% of it is remaining, how can we write that? Yeah, 3/4 A or 0.75 A. Either way, great. We haven't plugged it in yet. We will. Okay, so your original sample, that's your initial value. Okay, this is what is going to be remaining. Okay, so this is remaining. This is initial. And so we're going to plug this in to find t. So we're still going to be using our decay formula. Okay, so our y value, our remaining value, okay, is going to be the 0.75a. Okay, so the remaining value is y. The initial value is a. And then it's still multiplied by e. And then your k value is given. Okay, they give you the decay constant here. This is your value of k. There's 1, 2, 3, 4 zeros. 1, 2, 3, 4, 2, 8, 7. And the reason why I said you can use the A's is because what's going to happen? If you want to get this by itself, what are we going to do? Just divide. When you divide by A, those will cancel. Okay, and if you wanted to use a different value for A, if you wanted to choose a value, it'd be the same thing, right? Use 1, P1 and 0.75, bless you. That would be fine, all right? So you have some leeway there. All right, we know when we get E by itself, we got to bring in that natural log. So the natural log undoes this value. Okay, and then we just have to divide by the value in front. Okay, it does tell us to round to the nearest year, which means you're going to round to the nearest whole number. And then Kayla, will you tell me what you get when you calculate this?
I get 10,024 years.
Good. Okay, so when you guys did it, you should see the 10,023.7. So 10,024 years. Which is why we don't like radioactive substances. All right, do you guys want to try B? The language is a little bit different. Okay, so find how long, so we're finding the time again, it takes to lose 75% of the original sample. Yeah, so there's 25% left. Okay, there's a reason why I did these, because you're going to see these in your homework. Okay, and I want you to understand the difference in the language. Okay, so if you're losing 75%, Okay, if you are losing 75%, remember that means you have 25% remaining. Okay, so that's what's going to be plugged in for your value of y. Okay, the y is how much is remaining. Okay, so like I showed you with this, your a's just are going to divide out. So if you just want to write the 0.025 equals e to the negative 0.1234287. Okay, you can do that and then just go ahead and round to the nearest year. Okay, the more you practice this, the easier it's going to become. It is very similar process over and over again. And then, Jack, when you get your final answer, will you tell me what you got?
48,303.
Yep, 48,303 years. Yeah, so you got the 302.9, and that's how it's going to round. Okay, so your 8.5 is mandatory. I know. Pause for groans. But this chapter 8 tests tends to be one of the harder ones just because logs are brand new. Okay, so it's really important that we have this practice, especially with these story problems. No, but you're going to be using this factor. All right, and then I'm also going to put the answers to your homework